You know, we see it all the time. Your weather app says there's a 50% chance of rain. A project manager promises a 90% chance of success. But have you ever stopped to think about what those numbers actually mean? Well, today, we're going to break down the real logic behind the numbers we use every single day.
It turns out the answer is way more interesting than you might think. And to really get to the bottom of it, we have to tackle two really big challenges that are right at the heart of probability. So what are those challenges? Well, first, we've got the problem of meaning. And second, we have the problem of consistency. If you can get these two right, you've pretty much mastered the logic of chance.
Okay, let's break that down. First, the meaning problem. We have to ask ourselves, what does a number like probability even represent in the real world? Is it a physical thing, a state of knowledge? And then there's consistency. How do we build a system of math with unbreakable rules so that our calculations always make sense and we don't end up with totally impossible results like, say, a 120% chance of success?
So to tackle that first problem, the problem of meaning, we're going to look through three totally different lenses, three different philosophies for thinking about what chance really is.
First up is the classical interpretation. This is the one we all learned in school, and it's all about pure logic and symmetry. Think of it like this. If you're designing a casino game, you need to know the exact odds. For a perfectly fair die, this approach is clean, simple, and, well, perfect. Each side has an equal 1 in 6 shot.
But what happens when things aren't so perfect? What about a loaded die or some really complex system in the real world? That's where the relative frequency interpretation comes in. This is the experimental approach. You don't assume the odds. You go out and discover them. If you want to know how often your algorithm is going to fail, you run it thousands of times, and you just see what happens. Probability becomes the result you see over the long, long run.
And last but not least, we have the subjective interpretation, which is a whole different ballgame. This is what a doctor is doing when they say, I'm 90% sure this treatment will work. They're not talking about thousands of identical trials. They're putting a number on their own expert intuition. This is the whole idea behind Bayesian thinking, where you start with a belief and then you mathematically update it as you get new information.
Now, each of these views has its pros and cons. The best one to use really depends on the situation, and choosing the wrong one can be a disaster. I mean, imagine trying to predict a new aircraft's safety using a classical model. Impossible. Relying only on frequentist data? That would mean you'd have to literally crash thousands of planes to get it. No, you need the subjective expertise of engineers to build those first models. The stakes couldn't be higher.
So we have these three different ways of thinking about what probability means. But here's the really crucial part. No matter which philosophy you choose, whether it's logic, data, or belief, the math has to follow a strict set of unbreakable rules. That's how we keep everything logical and consistent.
These rules are called Kolmogorov's Axioms, named after the brilliant Russian mathematician Andrei Kolmogorov. And get this, there are only 3 of them. Just 3 rules, but they are the entire foundation of modern probability theory.
Let's walk through them real quick. First, non-negativity. This just means the probability of something happening can't be negative. Simple enough, right? You can't have a negative chance of winning the lottery. Second, normalization. This says the total probability of all possible outcomes has to add up to 1 or 100%. If you flip a coin, there's a 100% chance it's going to land on either heads or tails. And third, additivity. For events that can't happen at the same time, their combined probability is just the sum of their individual ones. So a 1 in 6 chance of rolling a 1 plus a 1 in 6 chance of rolling a 2 gives you a 2 in 6 chance of rolling either 1.
These 3 axioms are so much more than just abstract ideas. They are the fundamental sanity checks of probability. Seriously, every single theorem or rule you've ever used comes directly from these 3 core principles. There would stop the math from going completely off the rails.
Now, I know these axioms can feel a little abstract. So to make them feel totally intuitive, let's use a super simple analogy, a computer hard drive.
Okay, so just picture a 1 terabyte hard drive. The total size of that drive is like our sample space in probability. It contains everything, all the possible outcomes, just like the drive's total capacity holds all the possible space for your data.
So, just like the entire drive represents 100% of its own space, the probability of the entire sample space, the chance that something from our big list of possibilities will happen, is always 1 or 100%. That's axiom number 2, normalization. See? It just makes sense.
Now let's look at axiom number 1, non-negativity. This is just common sense with our hard drive.
Could you have a file on your computer that takes up negative 500 megabytes? Of course not. That's impossible. Space can be zero or it can be positive. And in the exact same way, probability can never be negative.
And finally, additivity. Imagine you have two separate partitions on your drive. They don't overlap. Partition A is 100 gigs and partition B is 200. Well, what's the total space they take up? It's just 100 plus 200. This is exactly how the third axiom works for events that can't happen at the same time. You just add their probabilities together. Simple.
Okay, so we've explored the different ways to think about what probability is, and the strict rules that govern it. Now let's bring it all home and see why this stuff truly matters for engineers and data scientists out there in the real world.
Everything we've talked about has a direct practical use. When engineers simulate network traffic to figure out failure rates, they're using that relative frequency idea, running thousands of virtual tests. When a spam filter gets smarter, it's using subjective or Bayesian probability to update its beliefs with new data. And those axioms? They are the ultimate sanity check for designing any reliable system.
And this, right here, is the bottom line for anyone who builds things. If your algorithm for calculating a machine's reliability spits out a probability of negative 0.5, or maybe even 1.2, you don't have to go digging through lines of code. Kolmogorov's axioms tell you right away, with 100% certainty, that your code is buggy. Your math has broken the fundamental rules of reality.
So let's wrap this up. The mathematical rules of probability, the axioms, they're universal. They are non-negotiable. But the meaning of probability, how we connect it to the world, is still up for grabs. Which leaves us with a final question for you to think about. In your own work, in your own life, which interpretation of reality do you trust the most? Is it pure logic, hard experimental data, or is it that informed expert belief?